Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Welcome back. My name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is a continuation of an introduction to antiderivatives for a differential calculus class, or depending on the textbook you use, you might be running into this at the first day of your Calc 2 course. Whichever. Doesn't really matter. Same topic no matter what. You should have already watched my video on the concept and basic theory of antiderivatives. Now we're just going to go ahead and extend that so we can really evaluate the antiderivatives for a bunch of different functions. And that is all based upon this one little theorem. The antiderivative of a sum or a difference of functions is the sum or difference of their antiderivatives. I have never been a fan of language theorems like that, but I was the one who chose to write it that way. So let me give you the symbolic version of that. The antiderivative of f plus or minus g is capital F plus or minus capital G, where capital F prime is f and capital G prime is little g. That is, capital F is an antiderivative of little f and capital G is an antiderivative of little g. And the proof is actually very quick. There's not much I could really say about it. We'll start with the assumption that let's see, we have two functions f and g, and we have their antiderivatives capital F and capital G. There we go. Then we're going to go ahead and take the sum or difference of capital F and g. So look at this, capital F plus or minus capital G, but we're going to take the derivative of that sum or difference, assuming that these are functions of f. Now, since derivatives are limits, you can split limits across summation or subtraction as long as those limits exist. And we definitely know these limits exist because f prime exists because capital F is the antiderivative of little f. That is, capital F prime is little f. So we definitely know these derivatives exist separately. And that is just capital F prime of x plus or minus capital G prime of x. But we know that capital F is an antiderivative of f, so therefore capital F prime is little f. And same thing about capital G. Capital G is an antiderivative of little g, so capital G prime is little g. Thus, if somebody hands us a function, f plus or minus g, and we know, by the way, that the antiderivative of f is capital F and the antiderivative of g is capital G, we've just proven that the derivative of capital F plus or minus capital G is little f plus or minus little g. That is, capital F plus or minus capital G is the antiderivative of little f plus or minus little g. So thus, capital F plus or minus capital G is the antiderivative of little f plus or minus little g. And we have then shown the antiderivative of little f plus or minus little g is capital F plus or minus capital G. So we have actually shown that. That's it, QED. Not very much to that proof, honestly. A little bit too simple, just because when proofs are that simple, it almost is elusive to see how that works. But there we go. All right, let's use this. Find the most general antiderivative of this function. Just like when you were taking derivatives on the first day of learning derivatives, you could not take the derivative of this because you didn't know the product rule, nor did you know the chain rule at the time. So what we did at that time is we multiplied everything out. And that's exactly what you're going to do here. You're going to start with the fact that this is 2x squared. Let's see, plus 2x minus x, so plus x minus 1. Double checking my mathematics really quickly. Yep, that's what it is. And now we will state the most general antiderivative. So capital F of x, the antiderivative. Remember, the antiderivative of x to the nth power is going to be x to the n plus 1 over n plus 1. Let me just write that off to the side. And remember, n cannot be -1 because that would be 1 over x, and the antiderivative of 1 over x is the natural log of the absolute value of x. Now remember, when you're hunting for the antiderivative, you're really asking yourself, what would we take the derivative of to arrive at this function? I'll scoot that off to the side a little bit further. That's perfect. All right, so each piece of this, or every term of this, I'm going to ask that question. The 2 doesn't actually matter. I'm going to leave the 2 out front. What would I take the derivative of to get to x squared? Well, x cubed over 3. That's what I'd take the derivative of to get to x squared. Plus, what would I take the derivative of to get to x? X squared over 2. Again, raise the power by 1 and then divide by that new power. What would I take the derivative of to arrive at 1? Well, you take the derivative of x. And then plus c, because it's the most general antiderivative. You might want to write that as 2/3 out front, but that's the only adjustment I would make on this. What's nice about antidifferentiation, you can always check your work. You can just take the derivative of this to check to see if you were actually right. F prime of x is equal to, right? So you bring down the power, that's 2/3 times 3, or just 2x squared, plus bring down the power, 2x over 2, or in other words, x. Derivative of negative x is -1. Derivative of c is 0. So it does work out. That's the beauty of antidifferentiation, which is a word. All right, let's do that again, but with this function right here. Each time I'm just trying to pick on other functions. So the antiderivative of this function, again, we just ask ourselves that very basic question. What would you take the derivative of to arrive at that? Well, let's see. Capital F of x, let me go ahead and zoom in here. And I'll keep that in our viewing window. Capital F of x. Well, I would take the derivative of e to the x to arrive at that e to the x. What would you take the derivative of to arrive at the cosh? Well, the sinh. And if you're in a class that didn't cover hyperbolic trig functions, shame on your instructor. And then finally, we have this plus 34. And this piece right here, let me point an arrow at it. I mentioned to my calculus students very often that calculus doesn't work very nicely with radical notation. So if you see that notation, trade it out for rational exponent notation. That's x to the 1/4. So we are going to add 1 to the exponent. So it'll be x to the 5/4. And then we'll divide by that new exponent. Now, I'm going to start by saying division, but in reality, division by a fraction is the same thing as multiplication by its reciprocal. So I'm going to multiply this actually by the reciprocal of that new power. That's just an easier way to do it. And then don't forget, you still have that plus constant on the outside. That's the most general antiderivative. And then just go through and clean things up if they can be cleaned up, that is. 5e to the x minus 3 sinh of x. Let's see, plus 34 times 4 is 121 36 over 5. So plus 136 fifths, x to the 5/4 plus c, and that is as good as it gets. You can't really do anything else with that. You're pretty much done. Technically, the sinh you can write in terms of e to the x's, though these first two terms would combine a little bit, but you would still have two terms. So there's no real change up in the size of this. That's it. Anti-differentiation, pretty fun. Let's do something a little bit different. And this is technically what I consider to be challenging for a lot of students for a couple of reasons. That secant tangent throws people off. But again, as long as you kind of have that mantra in mind, what would I take the derivative of to arrive at each of these functions here? Well, what would you take the derivative of to arrive at the secant times the tangent? Well, that would be the derivative of the secant, right? So r of theta is going to be secant of theta. You can kind of double check in your brain as you move forward. You could just ask yourself, what's the derivative of the secant again? Oh yeah, secant tangent, great. Minus 2, and then the antiderivative of 5 to the theta power. Now, that usually is the one that throws people off. So let's go off to the left-hand side here and just take a look at something. If I said, what's the derivative with respect to theta of just 5 to the theta, you would say, oh, that's an exponential function. So it's 5 to the theta, and then times the natural log of 5. That's the derivative of 5 to the theta. It's 5 to the theta, and then times the natural log of 5. A lot of people forget that. Well, that means that if I started with 5 to the theta, that's what we're starting with, and I want the antiderivative, well, let's see. I'm going to divide both sides of this by the natural log of 5. I'll get 5 to the theta is equal to, the natural log of 5 is just a constant. So I could say that's the derivative with respect to theta of, let me write it in bracket, 5 to the theta over the natural log of 5. Remember, natural log of 5 is just a constant, so technically I could take it outside of this derivative or I could keep it inside. It doesn't actually matter. But that is true that the antiderivative of 5 to the theta is 5 to the theta divided by the natural log of 5. And that will be somewhat, not terribly, but somewhat important. So let's go ahead and make that move here. The antiderivative, what you took the derivative of to get 5 to the theta, is times 5 to the theta divided by natural log of 5. Then this last one. This last one is sort of like a chain rule because technically we know how to take the derivative of e to the theta, but e to the theta minus 4, well, generally speaking, we would have done a chain rule. But you could take a wild guess and you could say, well, what if isn't the derivative of e to the theta minus 4 also just e to the theta minus 4? And you would be absolutely correct. It is totally true. So you could just write that plus c. If you want to see a really cool way of doing that though, let's go off to the side here and let's just look at e to the theta minus 4 for a second. You could break that into two exponential functions, one being e to the theta, the other being e to the negative 4. E to the negative 4 is just a constant. And now if I said, hey, I have a constant times e to the theta, what's the antiderivative? You would say, oh, the antiderivative is just that constant times e to the theta. That's what I would take the derivative of to get to that constant times e to the theta. And so the antiderivative is actually e to the negative 4 times e to the theta, or e to the theta minus 4. Anyhow, very fun. I like these examples a lot. The final example is just one that throws only a few people off, but I want to make sure everybody's on the same page here. Find the most general antiderivative of this function. The first part's not going to be a killer, right? We just constantly ask ourselves that question. What would I take the derivative of to arrive at this function? So let's see. The first part, capital F of x. We know the derivative of the tangent is going to be that secant squared. But the problem is that second part. That second part, you don't know the antiderivative of 2x to the 5th minus the square root of x over x. That's a bit messy. So instead, you're going to massage this problem a little bit. 7 secant squared of x, and you're going to break apart that fraction. That's 2 x to the 4th minus x to the 1/2 over x, or in other words, x to the negative 1/2. And now you can actually do this problem. Let's see, the antiderivative of 2x to the 4th, it's going to be 2x to the raised the power by 1 divided by the new power, minus antiderivative of x to the negative 1/2, it'd be x to the positive 1/2 because you're adding 1 to the power, divided by the new power, or another way to say it is multiplied by the reciprocal of the new power. That's another way to say that, plus c. And remember, you should just take a moment to clean up the statement. It doesn't take that long to say this is 7 tangent of x plus 2/5 x to the 5th minus 2 x to the 1/2 plus c. All right. So that's it for this video. There's really not much to anti-differentiation at the start, but in the next video, we're really going to get into it. The next video, we're going to start solving differential equations, very basic ones, but these are kind of the big problems in anti-differentiation, and they end up being very important in future levels of mathematics.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.